if you wish. We do sometimes this. So rho is separable if it lies in this cone, which we denote by set. And if rho is not separable, then it is said to be entangled. So why are we interested in entanglement? Well, how many people in the room will know it better than me? It's because quantum entanglement is a very important resource in quantum mechanics to carry out some tasks more efficiently than just using classical resources. So it's important to deal with quantum states which are entangled, but the difficulty is that it's NP hard to test. Given a state, is it entangled or separable? That's the need for criteria that can be checked efficiently. So this will be the main topics I want to deal with in the lecture. First, we will discuss some criteria for entanglement coming from the DPS hierarchy. Then we will see how this hierarchy specializes when you apply it to classes of states which have some nice symmetry structure, like being invariant under local diagonal unitary, so both symmetry. And this will make the bridge to linking to some other hierarchies which are more known, especially in linear algebra or in optimization, so hierarchies for classical forms of copositive matrices. And finally, if time allows, I want to deal with some even stronger symmetry properties in both symmetry, namely maximal symmetry, and see how this links with quantum definity type theorems. Okay, let's get started. So first I want to introduce a DPS here. So this is just recalling what is a separable type. There is, of course, a very well-known condition, which is a PPT condition. So what does it say? If we take a bipartite state, rho, so it's indexed by pairs, because there are two systems, so it's indexed by pairs ij, kl. So if it is separable, then of course it should be positive semi-definite, because every state xx star dot times yy star is positive semi-definite. So that's obvious. The second condition is that its partial transpose should be positive semi-definite. So the partial transpose here, you take the partial transpose in the second, the B register, means that you take the second indices, J, L, and you flip them, L, K, L, J. So this should be, again, positive semi-definite, and simply because if you apply it to a rank 1 state, this amounts to replace Y by its conjugate. So of course, this preserves positive semi-definiteness. So here is a simple example of a state. You just take the sum of the EI times its conjugate transpose. So this is obviously a positive semi-definite matrix, but it is not PPT. Because if you rewrite it in this way, taking the partial transpose means flipping the indices in the second factor. For ij becomes ji. And okay, let's just look at a small example for n equal to 2. So this is how the state W would look like. It has a 1 at position 1, 1, 2, 2. And when you take the partial transpose, the 1 is flipping to the position 1, 2, 1. So this one is PSD. This one is not positive semi-definite because 1, 1, but the diagonal is so the PPT condition is not satisfied, so W is entangled, and this is actually one of the maximally entangled states. It's very nice to look at the class of states known as the Brauer states, which you get by taking combination of the identity, W, and its partial transpose. And for this class of states, so this is a 3-parameter class, it can be shown that this knows that separability can be parameterized in fact by the PPT condition. So the PPT condition already suffices to characterize separability. If you set one of these to 0, you get the Weber state of the states. And what I want to mention is that these states are particularly relevant because for our lecture, because actually they are exactly the states which would be invariant under local orthogonal matrices. So orthogonal means that here you have an orthogonal matrix, and local means that your orthogonal matrix is actually product of two orthogonal matrices and the same copy of. And you ask that your row should satisfy these three-dimensional properties, and then those rows are exactly the power states. And later we are going to look at the similar invariance property, but instead of having invariance under orthogonal, we are going to have invariance under diagonal orthogonal, and also replacing orthogonal by unitaries. So replacing orthogonal by unitaries brings you to the vertical states and isotropic states, and we will see what happens when you allow a smaller group of symmetries, and we get a much richer class of states. So for n equal 2, the PPT condition is already sufficient to characterize separability, but not for n larger than 3. This is known. And so this is where the DPS hierarchy pops up. It enables to characterize in an asymptotic way the full separable cone. And it's generalized PPT. And I stress it asymptotically because we're never going to find a single semi-definite program which represents a separable cone, because it has been shown that this is not possible for LNP3. The best you can hope is to characterize the cone in an asymptotic way. So I should say, don't hesitate to stop me if there are any questions, please. Okay, so I guess maybe not everybody is familiar with the DPS cone, so I just give the detailed definition in this slide. So this hierarchy is the so-called state extension. So let's start with our bipartite state, OAB, which is separable. And now I want to say, well, if the state is separable, it must satisfy certain conditions. So this will serve as necessary conditions for characterizing separability. So what are these necessary conditions? So if your state is separable, it is a conic combination of these product states. Well, for simplicity of the argument, let's say that rho is just equal to 1 and everything works out linearly. So suppose the rho AB is of Z4. And let's assume that these x and y are scaled to norm 1. So that can be done with our generality. So then what we can do is to build an extended state. Pick an integer t, and we are going to build a new state, rho ABT, which will act now on, so it's going to be a Hermitian matrix acting on the product of CL. This is the A register, and the B register gets copied t times. And how do we do that? We simply take the B factor y star, and we take its tensor product with itself t times. So from rho AB, we get this extended state. And now what are the properties of these extended states? First of all, it is both symmetric in the T copies of the B register by construction. So the B copies are just all the same. So if you want the definition of the formula, it means that if you take a T index, the rows, the T index for the columns, if you permute them by tau for the rows, by sigma for the columns, you don't change it. But in other working on the first space, C to the n times the symmetric subspace of tensors in the B registers. So that's the first property, both symmetry in the T copies of the B register. The second property is PPT, but now its PPT is generalized. So what we do is we take a subset of the B register, let's call it S, for example, we take this collection, and we take the partial transpose with respect to a subset of the B registers. And as argued before, this just means you replace y by y bar, so the matrix stays positive semi-definite. So this is what the second condition says, is it should be positive semi-definite across all after taking the partial transpose under any subset of the B registers. And finally, if you trace out T minus 1 copies of the B register, then you get again a bipartite state, and you want to recover the original state. And taking the partial traces, so you have your big state, it has a block diagonal form, and taking the partial transpose amounts to taking the sum of the blocked diagonal blocks. Here is the formula, and this is a place where using the fact that you are normalizing the y to have not mass. So, in summary, what is the level T of the DPS hierarchy? It is a set of bipartite states which have an extended state of order T, satisfying these three properties. So by construction, for T equal 1, this is nothing but PPT. And if for any T we get an auto approximation of set, and if T increases, these auto approximations become tighter and tighter. So we get a hierarchy of auto approximations which get tighter and tighter around set. And if we take the intersection of all of them, we get the separable form. This is that of directly parallel stability, that if you take the intersection of all these auto approximations, you get the separable. Yes, please.
So how is this compatible with what we got on the previous slide? There was no S version.
Very good question. So what I said in the previous slide is that this infinite intersection cannot be omitted. There is no, in particular, there is no T such that set would be completely still. Another way to say it, if a state is not separable, then it doesn't lie the infinite intersection, which means that there is some level which will characterize entanglement. So for every separable, not for every integral state, there will be a level in the hierarchy with the properties that the state doesn't lie in the.
And this is independent of N.
You don't know the T in advance. So you have this is set, and you have the DPS. They get title and title.
For n equal to 2, they are of course for example. So
yeah, for n equal to 2.
And like for n equal to 3, could it be that there's a finite T?
So for n equal to 2, it's PPT, which is DPS function. For n equal to 3, we already know that set is not equal to DPST. For n, that's the point. Actually, this result for n equal to 2 is because I said n, but actually the result is for 2,3 set state PPT equal to set. But here I just decided to do n. So the original proof of this completeness, sometimes known as the completeness of the DPS hierarchy, follows using quantum definite theorem, as some work, of course. And what I want to do next is to give you a sketch of another approach to show it, which would be based on more on polynomial optimization tool, on the moment approach.
Yes.
Yes.
So you say that this intersection eventually becomes if you intersect all of it, and one really needs the infinite.
Yes.
Yes. And this means that like for every T there is something that sits outside. That sits. There is something that you don't get.
If something is outside,
I guess something.
It's going to be outside of one of these.
It's going to be outside there.
Yes.
I guess the question is that if I give you T, can you hook up in an explicit way the state for which DPS T that is not in set but it is in DST? Is it right? Because I guess the question is kind of the other way around. There is this
I understand. Yes,
there is an anti-hardness statement that says that there will be something for which the T has to be large, because otherwise you go against.
We know it. But getting explicit construction of this object is not so
It's hard.
easy. It's
Yeah, I
hard,
understand.
yes. So PPT entangled states are exactly the states which are in DPS1, which is PPT.
Uh-huh.
So that's a highest of all, which are here but not here.
Yes.
So there is actually a lot of literature constructing these PPT entangled states.
So it's already hard at the first level. Yes. Like it's
I mean,
already known
you-
legal at the
I
first
mean,
level.
But there are classes of states.
Yeah.
There are good classes of states. For instance, as I said in the beginning, the Brouwer states, we know exactly what are the conditions on the parameter which ensures that it's set. That it's so there you can say something. So for some classes of states with structure, one can say no. But in general, find a state which is in T and not in T plus one. This is it's a good question, yes. And the motivation for looking at classes of states which have more structure. So this has been a line of research in the literature. So maybe just one slide about how to give you an insight, at least for the people who are more from the polynomial optimization community, how to show this completeness. And also motivation is because it's going to give us hands on how to code this hierarchy in a more compact way. So the starting point, I will just be a bit sketchy, yeah? Please allow me. So the starting point is that our state is in the DPST level, if and only if there exists a linear functional acting on polynomials in XX bar, YY bar, be homogeneous of degree 2t. So 2 is in XX bar, 2t is in YY bar. And that's just a linear function. And if you have rho, how do you get L? Roughly by via this formula. If rho is in the DPST level, it has a DPST certificate, so there is this rho L. And now you define L via this formula. Roughly. And now we should look at what are the properties that L should satisfy, which would correspond to the properties of the extended state definition. So L should recover rho. The initial rho, if you apply L to this matrix. This big matrix should be positive semi-definite. So this would correspond to the PPT condition. Well, actually, to have it correspond to the PPT condition, one would need to observe, and it helps to observe that actually many of the entries of will be zero. So this big matrix will be block diagonal, and very roughly speaking, these blocks are going to be all the partial transpose across all the bipartitions. With the difference that before it was expressed in terms of in the tensor formalism, and now it is expressed in the polynomial formalism. So you have already got rid of a lot of overhead coming from the tensor formalism. What I meant here. So if you want to implement it, you rather implement this because you have already get rid of a lot of redundancy, if you wish, which is inherent into the tensor formalism. But this does not yet. So now maybe for the experts in the room, you would think, okay, I could have said also that L, so here it's on homogeneous, I could extend it to the full space by saying that my L is 0 on the ideal of the B sphere, and then I would apply Tutina theorem, which says that if you have a linear functional, which is positive on the quadratic module on the sphere, then L has a representing measure on the sphere. But this doesn't work because we only extend the Y side. So this doesn't work. So the way to fix it is to, instead of looking at linear functionals going to the scalars, we now go to the linear functionals going to the matrices. So we get rid of the X, we get this new linear functional acting only on the polynomials in Y bar, and it goes to Hermitian matrices via this definition. The exact detail is not so important, but this is how the XX star is taken to the picture. Now, we recover our original state. This is a positivity condition again. And we ask that our L is 0 on the ideal of the sphere. And now we get the proof of completeness by using the analog of Putiner's theorem for linear functional with values, with metrics, taking values in matrices instead of scalars. And this is a generalization which has been proven by Church and Zala. This is the two-line proofs. We take our state which lies in all the DPS relaxations. So for every t, I have such a linear functional LT, positive, 0 on the ideal, very roughly speaking. So very classically, this implies that. So you have for every t, you have an LT. Your LT is acting on polynomials of degree 2t, then 2t plus 2, so increasing. And you can show that this sequence has an accumulation point, which is now acting on the full polynomial range. And now we use the matrix valued theorem, which says that L has a representative measure, which has values in positive semi-definite matrices, and is supported on the sphere. And now, if you figure out what it means, you get exactly, since we are looking at it only on a restricted degree, you can assume that the measure is finite atomic, and you get such an expression which is exactly giving you the set number position. So I don't expect you have followed all the details, but what I wanted to try to explain here is that this construction, the DPS hierarchy, is actually the same thing as the moment approach for optimization on the sphere. So the completeness, which is classically derived via quantum definity, can also be obtained via the real algebraic results about moments of measures. Okay. So let's now step back. So I've introduced the DPS hierarchy. We have this DPS, this hierarchy DPST. And now we want to see how it adapts to special classes of states with nice invariant structure. And we start with local being invariant under local diagonal unitaries or orthogonal matrices. So just to set the notation, DU stands for diagonal unitaries, DO stands for diagonal orthogonal matrices. So diagonal orthogonal is just a diagonal matrix with plus minus 1 on the diagonal. And diagonal unitary is just a diagonal matrix with complex of norm 1 on the diagonal. Okay, so now this, bear with me, this is a mouthful. We just look first at the blue letters. So local diagonal unitary invariant states. These are the states rho which satisfy this equation. So here U is diagonal unitary, and you take the tensor product UU on the left side and on the that you are the invariants. So again, this local means that this unitary here is a product of two, and diagonal unitary is 6 points. And we use the same letters A, D, U, I, N for the set of states which has this invariance property. Now comes the red part, conjugate. Conjugate is the same definition, except that on the B register, you replace U by its conjugate. That's the conjugate. Then comes LDOE, for O for orthogonal, where instead of unitaries, you now take O for orthogonal. It's diagonal. I didn't figure out these definitions. Huh? They are in the literature. I see they are. So it seems that this falls out of the string. So, okay, last line was the source of the definitions, but it will be on the last. So this contains the The variance is isotropic and the ground states that we defined at the very beginning, where instead of diagonal, we were insisting all unitary or orthogonal. This is a much larger class. So let's, for instance, we can look now at the projection onto one of these space. And since we have invariance on the group, you get the projection by taking the average. So you average by integrating on two group. And an easy observation is that if rho is separable, then the same applies to these projections. So maybe it's difficult to deal with rho, but at least you can try to deal with the projection on one of these subspaces. And this motivates looking for more efficient implementation of the DPS hierarchy for these classes of states. So this is the original definition of the classes by invariance. And now this invariance property has as a consequence a very nice sparsity pattern on the matrices. So sparsity pattern means that these are matrices with a lot of zero, and these zeros are very well positioned. This will make such object block diagonal. So rather than looking at the exact indices which are here, okay, let's maybe look at, so the weakest invariance is LDO. This is where you have most entries, so less zeros, and it contains the other two. So those states are specified by, they are of size n squared by n squared, but in fact they are specified by 3 matrices of size n by n because of the sparsity pattern. So only non-zero at those places, So there are only non-zeros only at those ij, which you plug in this matrix X. You can have non-zeros at iijj, which you plug in this matrix Y. And you can have non-zeros at this ijji, and you make the blue matrix. So the whole state is completely specified by these 3 n-by-n matrices. And they have all the same diagonal by construction. Yeah, so somehow, yeah, move on. It's okay. But except that you know it's part of the formula. So the formula says that your state here, let's take the last one. Ah, thank you. Thank you very much. So the state depends on these 3 matrices and has a block diagonal structure. You have a block Y of size n by n, and then you have a number n choose 2 blocks of size 2 by 2, which are created by taking the X and the Z entries. And let's give it a name. I mean, these people gave it a name, C and Nishida. Let's call it rho indexed by this triple X1 set. And this is a class of states that we would like to understand how the DPS hierarchy works with them. So just for illustration, for n equal 2, we have a 2 by 2 block, that's a Y matrix. And we have a second 2 by 2 block. This. For n equals 3, here is how the state will look like. You have a red block, Y, of size 3 by 3, and then you should have 3 choose 2. Yeah, whatever. Okay, so the basic state, rho AB, has this nice block diagonal structure. And now it would be nice to see that if it is in the DPS hierarchy at one level, that it has a certificate which looks almost as nice as the original state. So the question we looked at together with Jonas is, does this nice sparsity or invariance factor, does it preserve, does it go to the higher level of the hierarchy, and this is what we can show. So for this, we just define the natural analog of CLDY, now we put a T, where we copy the B register by T copies of it. And our first result is if rho is in DPST and is CLDY, then rho has a certificate, a DPST certificate, which is CLDY structure. Moreover, such certificate is block diagonal. It has a block diagonal structure. Let's try to see how it looks like. There is complete characterization on how the blocks arise. And also the partial transposes all of them are block diagonal. For instance, for N is 2, T is 2. So here is the structure, the sparsity structure of the DPS group certificate with this invariance property. So here I set the invariance property for CLDUI. The reason was that I wanted to let's see that the B register was different. But of course, you have the same for LDUI. You just take a transpose, and also for LDOI. All this can be done in all the three settings. So let's just see now, okay, I'm claiming the DPST certificate is easier for CLDUI state or for this states with this nice diagonal invariance property. And how does it behave numerically? How do the block sizes compare? So let's generically, in the tensor setting, the DPST hierarchy would involve T plus 1 blocks, each of size n to the T plus 1. That's a state of affairs if we don't do anything. If we move to the moment setting, which means get rid of the tensor formalism and express everything in the monomial, in the polynomial settings, and you already get a lot of redundancy away. This would be how the numbers would look like. Now you would get the number of blocks, and these are the sizes. So you see already for n equal 5, T7, you already have 2 blocks of size 12,000. So still big, grows very hard, the sizes. But if you go to CLDUI states in the moment setting, then let's look only at the entry N is 5, T7. You are going to have that number of blocks, it's many blocks, but the largest block which will have size 1/7. So there is a dramatic decrease in the size of the blocks. And for SDP solvers, this is very important to have. Many blocks is okay, but they should not be too big. But of course, there is a limit. Too many blocks is also a problem. But at least this is not computable at all, but here we can start computing things. Jonas has implemented the numbers. So here is, for instance, an estimation, theoretical estimation that we can do on the ratio of the largest block size in the invariant case with respect to the generic case, and you see that it's 2t factorial divided by n to the t. So the reduction kicks in clearly when you do when you look at the invariance setting. So maybe just, so in the paper we have a small example, so it's a state CLDUI with just 2 matrices X and Y. The only thing I want to say about this is that we can actually characterize analytically membership in DPS2 because we know what are the blocks, then we can look inside the blocks and plotting symmetries and properties of the kernel, we can do an analytical characterization. But it becomes already tricky at the level T equal 2 because you have many blocks. Okay. So I've discussed the first invariance property, symmetry structure that you can put on your set of states, which is this invariance under local diagonal unitaries or local diagonal orthogonal matrices. Okay. Now I want to look at other class of symmetry that you can look at state, which is very well studied in quantum information, is being both symmetric. So I'm interested in Bs of Cn tensor T times, which is a set of both symmetric matrices, which are just in Hermitian matrices where all the columns are invariant to permutations of the indices, and the same for the rows. This.
Yeah, one question. So you showed that numerically it's slightly better if you project to these special invariant subsets, but do you not lose it by projecting?
Oh, of course you.
So what is the cost of this?
I mean, it depends what you. So what I showed is that if rho is separable, then its projection on CLBY is separable. So that's what is one of the lemmas. So now, if or if it lies in the DPST level, then also the projection lies in the DPST level, and moreover has this nice sparsity structure. Of course, it's only an implication, but the point is that maybe if you look at the full state, you cannot compute it at all, while if you do the projection, you can compute a higher level. So this is more of interest if you have a concrete state that you are trying to test for separability. Testing the full DPS level or level 3, maybe it's impossible, while you could do the level 4 or 5 when you project on CLBY or LBOI. This is not a new phenomenon, of course. In the quantum information literature, it's often known as twirling, this idea of projecting on some nice subspace to get necessary conditions. These are all necessary conditions that hopefully are more numerically tractable. So both symmetric matrices are just matrices which act on the subspace of symmetric tensors. And again, an easy observation is rho is in DPST and is both symmetric. Then it has a DPST certificate which is both symmetric. It's also not difficult to see. And which means that not only the T copies of the B register have this both symmetry, but all the T+1 copies have the symmetric property, including the L register. This also means that, I didn't write it, but it also means that both symmetric bipartite states which are separable are going to be conic combination of states of the form XX star, tensor XX star. So for the second, you take X equal 1. Then it makes sense to look how the whole thing specializes in this setting. And it specializes in the symbol DPS tilde T, which is the same as DPST, except that you have the both symmetry in all T+1 copies. This is a more symmetric, so it's contained in the initial one, and it's contained in the both symmetric state. And nice open question, actually, we do not know whether there is equality here. So this is actually a question about tensors. We know for T equal 1, it's equality because there is no tensor extension, there is no extension, but for at least already from T equal 2, we don't know because there is equality here. Of course, there is this hierarchy is complete for the separable both symmetric tensors. It follows from the general design. And here is the question I just mentioned. So these both, now let's marry the two structure property, both symmetry and being LDUI. And maybe, yes, maybe we look at this observation. So if your bipartite state is both symmetric and LDUI, this is known in the literature as being diagonal symmetric or as being a mixed Dick state. And Dick states are the states which come from the natural basis for the symmetric two tensors. Exact details are not too important, what's important to us is that it's both symmetric and LDUI. Combining both has a very nice structure. Actually. So they are LDUI, so they depend on two matrices. It should be X, Y, Z. So I put a dot because the Y is actually just a diagonal, so we can forget about it because the information is already in X. And the third term, Z, should be equal to X. So both symmetric LDUI states are of Z form. So actually they depend only on one single n by n matrix. And the connection which was already made in this paper by Johnson and McLean is that this state is separable if and only if the matrix X is completely positive, which means it lies in the cone of matrices of the form ZZ transpose, where Z is real, non-negative. This is making a link between the cone of separable state, living in n squared times n squared, with the cone of copositive matrices being n by n. And this is a cone which is well studied in optimization and in linear algebra. So we have link between this and this state and by n matrices, and now it's natural to ask whether there is a link between the hierarchy for this and a classical hierarchy for the C. At level 1, it's easy to check that the first level will correspond to precisely X being doubly non-negative, P is the n non-negative. So that would be the first level of a hierarchy. And now we want to see what's a link for any T. And for this, oh, I didn't see it.
No, I just want to wait maybe. Yeah, 1 more minute. More looks like it's.
So maybe I just say a few keywords. So it's easier to go to make the connection, it's easier to go to the dual. So on the primal side, we have quantum states and completely positive matrices. Let's say quantum state, SEP. On the dual side, what would be SEP star? This is all the bipartite matrices whose inner product with SEP is non-negative. Well, this has a very nice interpretation in terms of this polynomial is non-negative. So when you go to the dual side, you land into the world of non-negative polynomials. This is all classic, yeah, but Condensati characterize what is the dual of the DPST hierarchy with this nice formula. You take the polynomial with this factor y to the t times t, should be a sum of squares. And what we did, based on this Jonas, we did the analog of this result, where you replace the DPST by which is a symmetric, the both symmetric analog. And then, which roughly, instead of living X and Y, just moves. But, okay, let's remember this. Oh, yeah. And now, if you go to CP world, this would be this polynomial. You have a matrix, is in CP, it's called the dual of CP, and all these. It's inner product physics. So before we had X tensor of X, now we have Hadamard of Z with itself. And that is there. Make a long story short. Okay, long story short. We have here, so CP, the dual size is the copositive cone. We have a hierarchy of auto-approximation to the copositive cone, it's long known. And these are the cones KT. And this result here is making a direct connection between each level of the auto-approximation for copositive with the auto-approximation for the dual of both symmetric states in the DPST level. So this now makes a connection between every step of the hierarchy, while before it was only known at the end of the hierarchy. SEP versus CP or SEP star versus composite. And the proof is really, the essence is here. It's going from this polynomial, which is a sum of squares. It's a complex polynomial in XX bar. It's a sum of squares, if and only if it's real part is sum of squares. Now we're already in real polynomials. You end up with this matrix showing the form KT and so on. And you end up with this article. Okay, so I think I should, for the interest of time, the slides will be also. So as I just tried to explain how there are connections between tensors, polynomials, polynomial optimization, and quantum entanglement. And I think the different viewpoints bring new insights that can be very useful. Thank you very much for the information.
You already got many questions. Thanks for this very interesting talk. So there are even more questions or remarks. Monique? Please.
You have an idea of how much the emission requirements is restricting what you can say, like how much would still hold to remove them?
So you mean if instead of doing Hermitian efficiency, Hermitian complex, you just do real symmetry?
For example, or removing that, so just
Yeah, it's a very interesting question.
So
it's different. So like for instance, it can be that you have a Hermitian, a complex Hermitian quantum state, which is separable, but has sorry, I started again. It's possible to have a real symmetric quantum state, but now real symmetric, which is separable, but nevertheless does not admit separable decomposition with real atoms. That it needs all complex, that it at least needs some complex. Sorry, if I may just add, so if you start with a bipartite state which is real valued, your OAB is real valued, and you want to test whether it's in DPST. If your OAB is real valued, then you know that it will have, if it is in DPST, it will have a DPST certificate if it's real valued. So you can get rid of the complex at that level, but nevertheless, it could still be that if it is separable, that at the very end, for separable decomposition, you would need some complex atoms. So there is actually it's a good question because I think there is even some papers which talk about does real quantum information make sense or not. I mean, there are such discussions actually, whether we could restrict ourselves to real sets. Yes. There are subtle things, like at the very end, it is going from a complex Hermitian sums of squares versus real sums of, sure. Yes, please.
Do you know if this is different with water two parties?
Sorry, I didn't hear.
I get it out. Do you know if this theory can be extended to more than two parties, to three parties?
I think so. It could. Okay, now I'm going to be very bold. I mean, maybe I mean, you can set the definition, of course. If you have three parties and instead of doing U tensor U, you are going to do U tensor U tensor U. Jonas.
So probably encode the information of the matrices anymore, but we will need tensors.
Tensors, yes. Right. So so we debated with the indices for the two case. Now we should go to the indices for the three case. Yes.
There's another one there.
Is there a notion that we can measure the distance between, let's say, the T SVD, the set of T SVD and actual set of nodes? Is that like
Yes.
maximal
Yes.
distance that increases as a function of p.
Yes, it's a very good question. There are some results in the paper by Navasquez and courses. Well, he has some, I'm not going to be able to say very precisely, but he was said. And if you have your whole AB, it fills in what BPST, then it's here, it's outside, it is in BPST. Then there is a construction, maybe something like this. You trace out B out of this. Now you are acting with the subspecies, now you do the tensor for that with an identity. Now you have again a state. And then this is separable. You have to do some scaling, again, not very practical, but this is separable state and it is able to characterize the distance in some mode to the fiction as rho of one that exists there. So it's a very interesting question we need to and on the dual side, this would correspond to you have a polynomial which is non-negative. How far is it from being a sum of square on one of these relaxations?
Very good.
Yeah.
Other questions or remarks?
There is a notion of Hermitian tensors,
Permission tensors. Permission tensors. Permission tensors.
we have like a diagonal, like we always have double the number of next product, then like conjugates.
Okay, maybe once, I'm not sure I answered your question, but the last part which I couldn't do is this maximally symmetric matrices. So this is, you have an M, which acts on a Hermitian CT. And you say it's maximally symmetric. So if such an object is also, you can also view it as a 2T tensor. And such a thing is maximally symmetric, but the 2T tensor is symmetric. And actually, if this definition will only make sense or hold if you are in R. So then it will be symmetric. Otherwise, this will never happen. But for real matrices of that form, you can look at the bigger symmetry property, which is this maximally symmetric property. And then you can ask how far are you from being in the, yeah, I'll stop here. So maybe that also connects to the question you asked about real versus complex. So there are results by Doherty-Benner, which we have improved recently with Alexander Globanov. So these are this quantum definitive thing.
Okay, so if there are no more questions, I think we can thank Monique again.
Thank you. Nice. Yes.
Good evening.
We use this one. Yeah, we can see it.